Hello everybody, today we should be talking about Max Planck and the first quantum revolution. So his work was based on black body or cavity radiation. What is this black body exactly? Now black body radiation had physicists in the early 20th century really confused. So a black body is any body that absorbs all electromagnetic radiation into itself. Okay? So it's kind of like a hypothetical body. But the interesting thing happens when no more radiation is shown onto it. Then it starts radiating all that electromagnetic spectrum back on its own, in its own way. So physicists kind of like modeled the black body radiation using a hollow sphere. Okay, so they used to put electromagnetic radiation into the hole and then shut the hole and then open it again, and then the radiation used to come out and they used to study it. Hence the word cavity radiation. Now, the interesting thing about black body radiation is that this body will basically emit electromagnetic radiation from all across the spectrum, from all wavelengths and frequencies. So it used to have a curve like this. Okay. Now on the x-axis I've got wavelength, and on the y-axis I've got spectral density. This can be in a way regarded as energy or power, in a way, not exactly. It's basically, you can think of it as the amount of radiation per wavelength. So this means that if this is the wavelength that is maximum, that has the maximum spectral density being emitted, and this is blue, okay, let's say this wavelength is of the color blue, then the radiation will appear to be blue overall. But that does not mean that I do not have a red coming out, or I do not have violet radiation. I will have all these radiation, that blue will be the paramount radiation because this is the maximum. Now, they also observed that this curve changed when they used to increase or decrease the temperature of the cavity. So that's about black body radiation. So what is so mind-boggling about it? So by that time, Maxwell had laid down his equations on electromagnetic radiation and their properties, and basically they couldn't predict this curve using those equations, and it was a huge dilemma, especially the first part of the curve. As you can see, the first part of the curve has a steep increase and the second half is a smooth dip. They couldn't exactly model using their equation this part of the curve especially, and this became known as the ultraviolet problem. And Max Planck then saw this problem. He came across this problem while actually working for a company to maximize the amount of light emitted through the bulbs. So he was actually not even doing proper research. It was more for an industrial purpose, and he came across this problem. And he had a statistical mechanical background, and he was really influenced by Boltzmann's work. And he realized that this curve looked a lot like the Maxwell-Boltzmann distribution that is spoken about in an earlier video. And that's what he basically then applied the logic that Boltzmann applied on gases to radiation. Boltzmann was the first person to model gases using atoms. Okay, earlier people used to think that gases were a continuous material, but Boltzmann said otherwise. He thought that gases were made of tiny particles, and Planck wanted to do the same thing, but this time to radiation. He thought that he wanted to model it. He wanted to model electromagnetic radiation into particles. Now, by that time, they knew that oscillating electrons created electromagnetic radiation, and they thought that it was a continuous radiation. That an electron could basically emit 5 joules. It could also emit 6 joules. But it could emit all the numbers in between 5 and 6 joules. 5.53, 5.54, 5.7483 joules. No matter what number it is, the electrons will be able to do that. But Planck questioned that, and he said, what if that's just a wrong assumption that we've made? What if an electron can only, an electron that is, vibrating, can only produce specific quanta of energy? And what I mean by that is that in a specific amount of time, it can only produce, maybe this energy is maybe 4 joules for this electron. Maybe it can only produce integral multiples of 4. Maybe it can only produce 8 joules and nothing in between 4 and 8 joules. Or maybe 12 joules and nothing in between 8 and 12. And you know what? It worked perfectly well. For the first time, anybody had thought of quantizing energy, and it seemed to explain black body radiation perfectly well. That's when he came out with his famous formula, E is equal to NHV. Now this E stands for the energy of the radiation, V stands for frequency, and H is Planck's constant. Now, and N is any integral value. So this means that for any specific frequency, you can only get integral integers of H into V for the amount of energy that is produced by this electron. So that's about it, and this is the first time the word quantum started being used in the physics world, by the way. So this actually kicked off the quantum revolution, and then the greats came, Einstein came, Bohr came, etc., and they basically furthered this thought of quantizing energy into tiny particles. And thanks very much. So thanks and subscribe. I hope you enjoyed.